See, there's another intelligent man in the front row who brought his Macintosh too, although yours is pimped out more than mine is with all the decals. Want to raise it up for the camera and get a shot? And there you go. Thanks for having me. The reason I'm here in the area has been working with Dirk and others on an effort that you'll hear a little bit about on building a handbook of software architecture. My two passions, since I'm no longer dead, a year ago I went under surgery. It was open heart surgery to cure an aneurysm, so I was like dead for a while, which was not a cool place to be. So I'm back, which is really nice. A bit of a humbling experience in that process. When I was diagnosed with an aneurysm, every male in my lineage has this defect in their upper aorta. So I went through a CT scan, and I was laying there. It was a machine by Siemens, and I looked at it and said, damn, I know the guys who wrote the software for this machine. And they used the UML, so, well, I felt good, but it was kind of freaky just thinking how much software saved my life. So there are a couple of things that I'm spending my time on these days. The interesting thing about being a fellow, do you guys have fellow equivalents in Yahoo?
Just barely recently.
Just barely recently, okay. The interesting thing about being a fellow is that despite the bureaucracy of IBM, they give me incredible degrees of freedom to do what I think we should be doing for the best of the company. So as Nick D'Onofrio, who works for Sam Palmisano, said, you basically have two jobs as a fellow. One is to invent the future, and the second is to destroy bureaucracy. And there's a lot of the latter, so I keep myself busy on both fronts. But the two spaces where I've been spending a lot of my time are in the area of architecture and collaborative development. Today I'm going to talk about a little bit of both of those, but also more general issues of where my head is for some current trends in the state of our software space and the business of building software. On the architecture side, a lot of what I do in the field for IBM is I go out as an architectural mentor or an architect to help organizations transform the existing systems that they have. Every system has an architecture. Most architectures are accidental, not intentional, because they're born of the tens of thousands of decisions that individuals make along the way. And one day you wake up and say, oh, I have an architecture, and boy, is it brittle, and I need to change it out and do these things. So that's why we do these kinds of architectural digs. On the collaboration side, which turns out to be very related to it, most organizations I deal with no longer have the luxury of fitting all their developers into one room. Oftentimes they're across buildings, they're across cities, they're across time zones, across continents. And so the problem we're facing there is, how can you gel a team to bring them together even though that physically they may not be together? And it's not just the geographical distribution, but it's also the temporal distribution, where a team does something, they walk away, they've made those design decisions, and there's a bit of entropy that goes on, because when I make those design decisions, the code is the ultimate reality, but the code doesn't necessarily reflect some of the design decisions that shape that code, and they're in the tribal memory of those people. Tribal memory, you've got the guy from Survivor talking here later, so he can talk to you about tribal memory. Different kind of thing. So we're exploring things like what SourceForge and CollabNet have done, but also going a bit further and looking at maybe using virtual worlds as a place where people can meet and build systems. So I'm spending a lot of my time these days in Second Life. You can find me as Aleem Theus if you happen to be there. I'm really anxious to get, I'm going to do this, I swear. I want to buy some body parts and expense it and see what IBM does. We don't have a line item for this. We'll see what happens. Earlier this year, I was invited by the British Computer Society to give a lecture in honor of Alan Turing, their so-called Turing lectures. It's not the ACM Turing lecture. That's a different beast altogether, but this is Alan Turing a la Manchester and all that. So they asked me to speak about what I see happening in the current state and the future trends in the software space. And so you're going to hear a bit of that presentation today. It really all begins, in my perspective, on what Bjarne Stroustrup has to say. He observes that our civilization runs on software. We have built systems as an industry that are in the interstitial spaces of the world. And I believe in the coming decades, we'll reach the point of no return where, in effect, it's impossible for one to function in society without, in some way, touching the software systems we built. Now, that's Bjarne's perspective, who is obviously an insider in what we do. Let's look at a very different gentleman in this case, Lech Wałęsa, who was the former president of Poland. And he observed this upon his first visit to Western Europe, in which he said, ultimately, you all have so much. There is such abundance here. You have so many computers. Why don't you use them in the search for love? Now, I don't think he's talking about MySpace or things like that. Yahoo Personals, sorry, Yahoo Personals, thank you. Which is vastly superior than MySpace in so many dimensions. So you have this interesting tension between what we know as insiders that can be done in our technology and those folks who are users of what we do that don't necessarily understand, oh, thank you. You are most kind. This is vodka?
Yeah. That's a martini.
Oh, oh yes, that's much better now. So you have this interesting tension between knowing what we can do inside and yet the social pressures that come upon us. And especially as we produce systems that are more and more facing to the general public, it's not just the technical issues that shape us, it's also the social, the moral, the ethical issues, which are things that we don't often talk about or teach in our schools. To that end, there are obviously some amazing things that we as insiders know we can do with software systems. We know that software-intensive systems can amplify human intelligence. We know that software-intensive systems can fuse, coordinate, do all sorts of things with information. But at the same time, it is the case that we know that software-intensive systems will never replace human judgment, and they're never going to create knowledge. So there are indeed some limits to what we can do in software. Not everything we want to build can be built. There are some very practical limits to the things we want to do. I was doing some work for Homeland Security not too long ago, and they have an interesting problem. I mean, you guys may complain of the siloed systems you have. This is an example of siloed systems where the silos are defended by senators. Senators don't understand software, pretty much. It goes hand in hand. So their idea was, okay, we've got all this data on all the bad guys, actually data on lots of people. Well, what they'd like to do, they said, is to sort of look across all these systems, tax records and motor vehicle records and passport records, and go search for signs of bad behavior. And at the very end, pop out a warrant for people's arrest. Now, I politely suggested to them that really offends me as a citizen, because I would prefer to have a human in the loop to deal with those kinds of things. But, you know, let's not talk politics right now, because you get me really riled up. So we know it's technically possible, but clearly there are some moral and ethical limits to what we should do in those cases. It's also the case they were going about it in a profoundly stupid way. They said, okay, we've got these silos. They want to impose a service-oriented architecture upon it. So they said, what we're going to do is to identify services in each of those silos and tie them together. And I said, that's really stupid. What you want to do is to look at the scenarios that cut across it, find the points of tangency, and that will be the place you probably want to plant some of your first services and build from that. So that's where they're trying to go, and hopefully not doing this, pumping out the warrant for their arrest at the end. So we know that there are some things we'd like to do, we can't do. It's also the case that there are some things we'd like to do that we probably shouldn't do. These are the moral, the ethical, those kinds of legal limitations upon our software systems. I was recently giving a keynote address to the ACM Special Interest Group of Computer Science Educators. And having worked with a number of universities in Asia and Europe and the US, everybody is telling me that the numbers are declining in terms of numbers of people graduating with computer science degrees. And it's absolutely frightening in that community, because they realize the problem is not just in the colleges, it's actually even starting earlier in the high schools, where we're teaching computer science to the degree of, that means people know how to surf the web and how to install the latest drivers from Microsoft Windows. Oh, you're a computer expert, therefore. Well, they've not begun to taught really any of the notions of the beauty and the elegance and the joy of programming. So part of what I've tried to express to that community, and you see that happening in groups such as what ALICE is all about. ALICE is an effort by CMU to bring sort of an interesting programming environment to the high schools that's fun and entertaining and engaging and actually attractive to the female population. It's not like, you know, building single-person shooter games, which may be fun for some genders, but not for all genders. So I'm a fan of Halo, by the way. I'm really anxious for Halo 3 to come out. But at any rate, in that community, and really through high school and on, we've not really taught much the beauty and the joy of software systems. And there is a deep elegance to what I encounter. Having done archaeological digs on a variety of systems thus far, it's amazing when you engage a conversation with the architects, because often they'll get very animated and say, oh yes, you know, here's this structure and here's this structure, and they'll just be wildly talking on the whiteboards. But a lot of that beauty is never expressed to the people that follow them. A lot of that enthusiasm and that elegance disappears when that person goes away. So what can we do, therefore, to expose that inner beauty? Another problem we faced is working with the Computer History Museum. If you've had a chance, go visit them. It's the coolest place. They're also becoming a museum of software. So there's a software curator, there's a software collections committee, and they're actively collecting software for preservation for future generations. If you think about it, it would be really sad if your children's children did not have the source code to Windows, for example, or other artifacts that have been created. It would be sad because we as an industry have produced things that have changed the world, and now is the time to keep these things. I was working with Dr. Dijkstra right before he died to get some of his papers. He died, and now we've got to go through the estate. So the problem is many of these early systems are simply disappearing from sight. The problem the museum faces is they've got all this gorp, all these tapes and cards and everything you might imagine. How do you expose to people the really cool stuff that's there? If it's a piece of hardware, you can show them, well, here's the Johnny-ac or the Iliac. Isn't that sexy and cool? If you say, well, here's the source code to, I don't know, Doom. Well, that's interesting, but show me the details inside of it. As part of the process of working with the museum, I was able to track down through Tim O'Reilly, who led me to Bill Atkinson, to get the source code to MacPaint. MacPaint is a beautiful piece of source code. It's written in Object Pascal. It's maybe 5,000 to 6,000 lines of code in its original form, and it's a beautiful piece of software. Beautiful in the sense that it's readable, it's easy to understand, it makes a lot of sense from just looking at the code itself. I had the opportunity then of working with both Bill and Andy Hertzfeld to do a video interview with them where we spent some time walking through the code, talking about their design processes. And it's those kinds of things that it's valuable for us to preserve because they represent the decisions that were made in systems that predated us that impact the systems that we have today. MacPaint, in many ways, led to the early versions of Photoshop, which is the dominant tool in that space. And you can see some of the similarities in the architecture from one to the other. Those are the kind of things we want to preserve. And so a challenge for us as an industry is how do we express an excitement for the people that follow us as to the beauty and elegance of the things that we have done. There's a conundrum with this, though, because at the same time there is beauty and elegance, it is also the case the software artifacts we produce are perhaps some of the most complex artifacts that humans have ever created. As I was telling Dirk and his colleagues earlier today, I was working with Cisco recently, and they have their iOS, their operating system, which originally started out being a 30,000-line program in, I think it was C and bits of assembly language. Simple, elegant thing, and in fact, the guy who wrote it, he's employee number 4 at Cisco. He's going to apparently donate it to the museum. The current version of iOS, in their words, consists of about 30 to 50 million lines of code. Now think about that for a moment. That's a delta of 20 million lines of code. So they know it's somewhere in between there, but they haven't really counted it yet. And that's a huge, huge delta. So they've gotten to the point where some of that early elegance is disappearing along the way. And it's a very, very complex system indeed. Very, very brittle system. Now, given that this was a lecture in honor of Alan Turing, there's a great book about him called Alan Turing, The Enigma. You'll learn if you read about his life, his was a life very much of contradictions. And so I'm going to talk about the contradictions in his life in a moment, but let's talk about the contradictions in our world. Now, these are the things that we as an industry face. You may not individually as you cut code once you leave here, but they impact us all in a very global way. On the one hand, the internet has changed the way that individuals collaborate. No doubt. Bit by bit, we have changed the way the world works. And yet at the same time, it's created an environment in which terrorism and other kinds of fraud and other criminal activities can flourish. How do I balance those two off? How do I weigh the good against the bad? The web provides unprecedented mechanisms for social networking. It also provides an incredible way for exploitation of children as well. How do I balance those two off? Do I go as far as what China has done and force every blogger to register themselves with their real name and have an army of people that watch over what they write? Is that the right strategy to go, or do we want something looser that allows these kinds of things to happen? It's also the case that software-intensive systems permit real-time and distributed access to information. I've got here in the bottom left-hand corner a shot from, I think, Davis Network's site for where you can buy a weather system and sort of put it on the web and show your local weather. Thank you for that musical interlude. And when I gave this lecture in London, they were particularly interested in this aspect because of the surveillance that pervades throughout London. Virtually every street corner in London has a video camera on it. And those video cameras go God knows where. And therefore, if they're searching for the bad guys, the government is investing a great deal of money in facial recognition, real-time recognition, to be able to track people. Latest word is that the UK is now actually putting surveillance drones across their cities. Is this a good thing or a bad thing? In the presence of real-time facial recognition, being able to track people, well, if you have a bad guy out there you want to track, that's probably a good thing. If you don't, well, there are limits upon what you'd like that information to go to. Last week I was in New York, and among other things I was working with the CIO's office for the city of New York. They are along a similar path, and so I sat down with one of the people in the office who leads child services. You've seen Law and Order, and you see some of the plots where they lose a child in the system. The guy said, this happens. They probably have 50,000 children who were in the system at one time, and they just don't have the mechanisms, the resources to track the children properly. But they said, what would happen if we had cameras in all the corners attached to facial recognition software, so if an Amber Alert were raised, and we could then maybe notify all the people who have cell phones in the area to be on the lookout of this particular person and track that child, wouldn't that be great? Yes, it would, but we have to weigh that off with what we are sacrificing in terms of our personal liberties. It's also the case that email and other software-intensive mechanisms have increased the velocity of communication. But if you talk to historians, they are very concerned about the loss of an entire generation of history. People don't write letters to one another anymore. They send emails or send IMs. And so whereas today we can study individuals from the past because of the correspondence they have done, a lot of the correspondence we see among individuals is simply evaporating from sight. I mean, heavens, look at what's gone on in the White House currently with the evaporation of a number of emails concerning Karl Rove and the like. So, you can think conspiracy theory or not, but the reality is that the fact that it is in a digital medium makes it much more harder to access. On the other hand, it also makes things much more visible as well, too. Things like, David Hasselhoff being videotaped drunk in front of his children, there for the world to see. So there's an upside and a downside to these kinds of things. But historians are telling us it's not just the loss of information, but the fact that someday we may never be able to read these bits. The Computer History Museum has reels and reels of tapes from various places that simply are unreadable anymore. We know the magnetic dots are there, but we have no way to really recreate their format, so these things are lost. JPEG is known to us today. Will it be known for us 2 generations from now and people be able to decode it? I don't know. It's also the case that software-intensive systems create new forms of artistic expression. They allow people like Britney Spears, who have no musical talent, to make lots of money. And yet at the same time, we know that the music industry in particular is frightened by the prospects of what this means to them because of the fluidity of being able to take an artistic creation and with zero distribution costs being able to make it available anywhere in the world. It's obviously disrupting the existing economics of that system. Is that a good thing or a bad thing? It's probably a community that needed some change, but this is a community that resisted videotapes a generation ago, and now they're resisting digital release of music as well. So hard to say what reality might be. It's also the case that software-intensive systems have enabled and accelerated scientific research. Dr. Craig Venter, the gentleman behind the decoding of the human genome, and just consider the amazing things that have resulted from that. A lot of work that goes on in genomic engineering these days is very, very software-intensive indeed. By the way, there's another interesting ethical piece of it, and that's the patenting of genomic sequences. We now know we can identify them in software. Should I be allowed to patent those kinds of things? Don't know. At the same time, software-intensive systems have, in effect, enabled us to build systems that allow us to kill one another more rapidly than we could in the past. I'm not just talking cyber warfare kind of stuff, but the ability to build weapons of increasingly amazing destruction. And there is intense software, there's a software intensity to the next generation of systems that are coming out. Yes, smart bombs and the like are good things because there's less collateral damage, but the ability to optimize explosions and optimize the delivery of explosives, we're getting better and better at it, all because of software. It's also the case that software is at the very fabric of our civilization. It is moved into the interstitial spaces of our world. And so we, as communities living in this world today, are increasingly becoming completely dependent upon the software systems that we have. And yet, the software systems that we build are very, very fragile indeed. It's like the sausage maker. You may love sausage, but you never really want to study how it's made because you'll lose your appetite. So it is in software systems. If you talk to the people behind funds trading systems or ATM machines or any number of systems you might imagine, life support systems, it's amazing how fragile many of those systems are, and the fact that they do work as they do is, in some degrees, a miracle, truly is. Not to say that we've not gotten better in building software systems, it's just that even though these systems are in the interstitial spaces, we rely upon a lot of very fragile pieces. Alan Turing, this is 50 years ago, was an amazing individual who predicted a lot of what we see in reality today. And he had the observation some 50 years ago that we would get to the point where we could have software systems that would emulate humans. Now, the name Turing test actually does not come from Turing himself, but it comes from the book 2001: A Space Odyssey. So it's used in the conjunction of the discussion of the computer HAL. So that's where the term comes up. But Alan Turing had this notion that there was this game, a parlor game that was often played in England, where you'd put two people in a room, generally a woman and a man, and you'd ask questions of them. And the idea for the people in the parlor was to figure out which one was the man and which one was the woman by their written responses. He extended the game and said, what would happen if we replaced one of those humans with a computer system? He believed we could do that within about 50 years. Well, here we are about 50 years. And so, well, let's see, in effect, simulating the illusion of a mediocre intelligence. Well, enough about George Bush. But you can tell where my political bent lies. By the way, that's me speaking. It's not IBM or anybody like that. This is my personal opinion. I said it on tape. So send me nasty letters. Alan Turing also noted that there were limits. He saw even in his time that there were limits. They were profound and deep. He was very much constrained by the hardware systems that he had at his disposal. But he, being a mathematician, also realized that there are some fundamental limits, that there are some things he knew he could not do because of those mathematical limits themselves. In the end, Alan Turing's life was a bit of an enigma, a bit of a contradiction, because his work in cryptanalysis ultimately shortened World War II by a couple of years, according to a variety of historians. His work led to the breaking of the German Enigma code. Now, speaking of moral decisions, I don't know if you know this story, but they broke the code early enough. There was actually fear of telegraphing to the Germans that the code was broken. And so there were a number of instances where they had broken a communication. They knew that an attack was going to take place upon a convoy, and they intentionally did not notify the convoy and let it be destroyed for fear of releasing the news that the code was broken. So terrible ethical, terrible moral decision they had to make. They had the technology. They chose not to apply it, and so people died as a result of it. So Turing's work changed the course of the war. And yet, you may not know this, Turing was a gay man. And being a gay man in England in the 50s was not a pleasant place to be. At the end of his life, he had a live-in lover. His house was broken into, and he reported it to the police. And during the discussion of that with the police, he admitted to them that he was homosexual. And because of the sodomy laws, he was immediately arrested and put into jail. And ultimately, he was chemically castrated, and he died. He committed suicide because he just couldn't handle it anymore. So a very sad contradiction in that he saved the country, and yet ultimately the country kind of killed him in the end. Interesting contradiction. Turing did so many things in his lifetime. He wrote papers on artificial life. He had ideas in what today we know as quantum computing. This is stuff that predates Feynman's work in that area, which is just sort of the fundamentals of that space. Of course, the notion of the Turing machine and the Church-Turing thesis beginning to tell us some ideas of the limits of computability. Ultimately, what Turing realized is that things that are computable, therefore, are possible, but there are some things in the real world that are possibly not computable and therefore are never possible for us to automate. Those are the limits that he saw. Now, let's bring these all together and talk about these notions of the limits. It may seem a little bit academic, but it turns out that in a number of systems, people encounter these limits daily. Some of these things are very fundamental, meaning that they are at the very core of the way our universe is structured. Some of these things deal with the human issues. And I would dare say that most of the problems you face in taking your ideas and your vision and turning them into raw running code, my guess is that for Yahoo, most of the problems lie in the area of design and organization. And I'll talk about those in a little bit more detail. So, working with JPL on one of their deep space probes, Barry Bain told me this story a few years ago, and it happened to me. They said, okay, we're going to build this thing that's going to go fly past the solar system. And by the way, we can only put X lines of code in it because otherwise it will weigh too much. And I said, wait a minute. That doesn't make sense. And they said, oh, yes, it does. Because we have this rule of thumb that says if I have X lines of code in C++, it translates into Y bits of object code. Those Y bits of object code have to be blasted onto some storage device. And there are only a certain number of space-qualified storage devices that we can use. Ergo, there is a weight associated with software. It gets worse because there's heat associated with software as well. Whenever I compute, it follows the laws of thermodynamics. So as I compute, I cast off heat. And if I'm doing a deep calculation, I actually may heat up part of the spacecraft too much. And so I may have to program the spacecraft to rotate so it's on the dark side and therefore cool it off. So therefore, if I'm building these kind of systems, I've got to worry about weight and heat. Can you imagine doing that as you're thinking about the software you're writing? Oh, can't do this. It's going to be too hot for them. Another system I've worked with are the people who build the software for the global positioning satellite systems. The satellites are in geosynchronous orbits. They are high enough, they're far enough away such that speed of light delays cause problems, and they're moving quickly enough that the Lorentz equation stuff kicks in. It's the dilation of time and length. So as you write code to compensate for the movement of the spacecraft, you actually have to compensate for those relativistic effects. Happily, you don't have to do that either, I would imagine. FedEx and UPS are in this situation where there are laws of software that bump into them. On an average day, FedEx has about 15 million packages in flight. And at Christmas and Thanksgiving, it's absolutely crazy, but that's on an average day about 15 million. And that goes to about 10,000 or so major points of destination. If I have maybe 10 packages going to 10 cities, I can brute force figure out an optimal distribution for those. I can't do it with 15 million packages in 10,000 cities. So you've got to get a good enough solution. This is a case where UPS and FedEx bump into the laws of software. There aren't enough seconds in the universe to calculate an optimal path. So what do? You do a number of things. You step outside the problem and try some genetic algorithms to get a good enough solution. You try some neural nets to get to a convergent good enough solution. Or you talk to the humans that have been routing things for a while and follow the well-worn footpaths that they have already done to give you a good enough solution. In either case, you don't attack the problem head on because it's insoluble, but rather you do something a little bit different. Now, moving up from this space is the challenge of algorithms. And I'd like to illustrate this by an example that comes from a trailer from Halo. Hopefully this will show here. Let me see if I can make this work. See, this way I can write off my purchase of Halo as a business expense. Is it going to work? Yes. I don't think you'll hear the video, but it's just a lot of banging and such. Oh, yeah, it is plugged in. But at any rate, what I want you to take a look at is the images you see here, and tell me what you don't see. So this is the Master Chief. He's doing some cool things. He's got some spacecraft there. He moves about. Oops, he's got a finger right up his nose. And it's incredibly photorealistic, but what you don't see are faces. If you study the history of algorithmic development in the motion picture industry, or actually of all the computer graphics, the first thing we sort of solved was how do I render a teapot? That was sort of the classical thing that you'd see. And that led us to Jim Blinn and his work on ray tracing algorithms. Then the next step was, how do I render a teapot that doesn't look like it came from a Barbie doll set of some sort, i.e. non-plasticky surfaces? So we worked on textures, algorithms for textures. The next level up was, how do I get motion into these things? Because static objects are interesting, but they don't really give us a sense of reality. So kinematics was part of the role next. And then the next level up was solving the problems of fluids. How do I make water look real? Titanic is the place where Digital Domain really honed their expertise in algorithms for water. If you look up close for some of the scenes of the ship, and you know the ship is computer generated because don't want to give away the story, but it's sunk. But if you look real close, you can see it's pretty gnarly as you look around the bow of the ship. They didn't quite get it quite right. But if you look at their more recent movie, The Day After Tomorrow, it looks very, very real. So they've got the algorithms down. The next breakthrough was in the algorithms associated with clothing. There's a scene in Titanic where some of the first clothing algorithms were used. John Cameron has a reputation for being, well, not a very pleasant guy. And there was this one scene where Kate Winslet is standing there. It's the bit where it's right toward the bow of the ship where she's doing the I'm the king of the world kind of thing. Was that Larry Ellison? No, that wasn't Larry. That was the Titanic. But I get those two confused. But she's got this scarf whipping in the wind, and Cameron didn't like how the scarf looked. So he said, get rid of it. And so Digital Domain had to build some new algorithms to actually replace that scarf with a digital one. So look closely, but her scarf is not real. It's completely computer generated. And they worked on it, a number of other people did, and now we've sort of gotten the breakthrough of algorithms for clothing. The next big breakthrough is for facial recognition. And we haven't quite gotten there yet. Things like Final Fantasy IV, if you've had a chance to see it, it's really good for static images, but once the images start moving, then you realize, oh, this is not quite real. So there's work to be done, but we're very close. So at any rate, this is a limiting factor for certain classes of problems. Not knowing the algorithms that enable us to do these kinds of things prevent us from taking our vision and turning it into reality. The next level up, whoops, got to move my cursor here. The next level in the problem of the limits between vision and reality is a corollary to the problems of algorithms, which is the problems of distribution and concurrency. The average developer does not know how to build good, concurrent, secure, distributed systems. They really don't. It is a wickedly hard problem. It's wickedly hard just building single-threaded systems. But if I'm building something where I have multiple threads that interact with one another, terrible problem. A good example of where we see some spectacular failures happened a few years ago when in London, in England, I guess that is in London, in England, the government put out a system that enabled all of their citizens to go online and look at their tax records. Very reasonable kind of thing. But very soon after, like the first day, people were realizing, oh, I can get online and I can see the tax records of everybody else who happens to be logged in at that time. This was not a feature. Because what had happened is the team that did the basic web-facing stuff did all the right things, but then there was another team off of here who did some of the caching stuff to make it go faster. They weren't talking to one another well enough. And so what happened is that the caching algorithms interfered with the user experience so that I could look into other things of people who were online at the time. Not a good thing. But it's something that they could not have anticipated. Well, they could have anticipated if they'd run some reasonable systems tests, but none of their individual developers saw it as a problem because it was not within their scope of the problems that they were solving. The problems of distribution, I love this one here, it's one in which the failure of a computer you didn't even know existed can render your computer unusable. And especially as we move to service-oriented architecture kinds of things, where I'm building services that I have no control over whatsoever, and I'm building systems that depend upon them, how do I build systems that are therefore reliable? That's a problem for many organizations. Now, I'm in the place where this is probably affecting or keeping you awake at night, the problems of design and organization. As I mentioned, every system has an architecture, although most architectures are accidental, not intentional. Very few architectures are intentional, except in those cases where I've had an opportunity to look at an old one, blow it up, and start over again. You are in a situation like so many where you have a continuously evolving software system, meaning you can't turn it off. You would have people outraged if you did. You'd have shareholders who would be sending lawsuits your way. You have unleashed the beast, and now you can't unplug it anymore. So the challenge, therefore, is how do you keep continuously improving what you're doing, because there are forces outside of you that you can't stop. Greater demand for capacity, greater demand for various kinds of services, further global distribution, these kinds of changes of technology out from under you that you can't control. These things are happening, therefore the problem you face is, how do I take the systems that I have today and continue to transform them so they continue to get better and better over time? You can't do it overnight, but you have to do it incrementally and iteratively through successive refinement of those architectures. When I go in and do an archaeological dig, there are a handful of questions I will ask an organization to give me a sense for how that group smells. First thing I'll ask them is, tell me about your rhythm of releases. Do you have a regular release strategy? And in some cases they'll say, no, we don't. It sort of happens when it happens. And you kind of work on that problem first. Because if they don't have a regular rhythm, then it says to me they've got a chaotic development process. They've got one that's opportunistic, that does not therefore integrate the activities of the people other than the software developers themselves. Then I ask them a little bit more about the frequency. Some may say, oh yes, it's regular, but it's every 6 months. And generally that's not going to be fast enough. You talk to the Microsoft Office team and they'll say, oh, it's every day. And that's pretty stupid, because it really is. The reason is because it never gives you an opportunity to step back and make anything simple. You never have the opportunity and the degrees of freedom to say, I really don't want to check this in today. I'd really like to check it in later in the week so I can step back and think about it for a while, throw some things away, and rip stuff out, and then I'll do it. But they're under such a frantic pace that there's this tremendous culture that says keep adding features and features, which is why Microsoft Office is going to consume all the bits in the universe one of these days at its current path. Another question I'll ask the group is, do you have an architect? And happily, I'm happy to report, Yahoo, you've answered properly in that regard. You have not only architects, but you have the right architecture organization that I've seen repeated elsewhere, where you have lots of different properties, as you call them, lots of different assets. The way to organize those is to put up an architecture board that has representatives from each of the architects of those groups working together. The wrong way to architect it, I see in some places, is where you have an architectural group over here that's not associated with any running project. And so you end up with people who are generally the people who are, they're there because they aren't good enough to be on a real project, I'll politely say. And furthermore, they are so disjointed from the real problems that they're building things that nobody will care about anymore. And this, by the way, is the structure of DISA, which is the architectural organization for the Department of Defense. So your tax dollars at work. We're working on it. The next question I'll ask is, do you have a culture of patterns? So I'll begin discussing with the group and see if they start talking to me in a language of patterns. And if the answer is yes, they start talking some of the Gang of Four stuff, then we'll go to the next step and start digging out some of their new patterns. When I was doing archaeological digs with the Photoshop folks, it's really beautiful architecture when you get to the core of Photoshop. There are all this other gorp around it. But you understand those basic abstractions and a handful of patterns around it, and you've got the guts of Photoshop. You really, truly do. But what I found in working with the Photoshop architects, they didn't have names for some of these patterns. They had them. They were certainly patterns, but they had no names. So we've been in the process of trying to find names for them. You too can have a pattern named after you. The next problem is the problem of organization, because it's not so much a matter of just how do I build these things from a technical structure, but how do I organize my people to be successful to work against those systems that I've architected? Reality is I am building things that can no longer have all the people fit into one room, so I've got to deal with the problem of temporal and geographical distribution. I'm often dealing with, on the average developers, so that I have average skill sets. My architects, who are perhaps my most senior and most experienced people, are going to be so busy they have very little time to continue working with the projects they've worked on. We see this happening in the Eclipse Foundation. And the original Eclipse architects, Dave Wiggin, Eric Gamma, and others, they were on task with Eclipse for the longest time. They've gone off to another project now, and in Eclipse, there is an Eclipse architecture board, but you can already begin to see some architectural degradation happening in Eclipse because there's nobody really watching over the architecture, and that tribal memory has not been communicated to the people who are now maintaining it. In fact, if you look at the documentation for Eclipse, there are these high-level vision documents and code and some detailed documents and lots of PowerPoint in between. So there are no real design or architectural documents that exist except in the heads of a few people. So one of the reasons why we're trying to extract the architecture of Eclipse. And I'm going to skip over the next of these because they deal with more legal business kinds of limitations. There are some cases where we know we can build systems, but we may not be able to afford it. And therefore, the raw economics of what we can build, it will impact moving from our vision to reality. Interesting thing about this particular equation, because this comes from Barry Bame's work on his Kokomo 2 model. I would imagine you don't do a lot of formal costing estimates here by any means. But what's interesting about this equation is that having looked at hundreds of projects, Barry's noted that the major factor that impacts the performance of a project is its complexity. Whatever you can do to alter the complexity of a system in terms of its raw size will have the most dramatic impact upon time to completion or the cost to complete itself. Furthermore, process is an exponent. So Barry has observed that a bad process amplifies complexity, whereas a good process can dampen complexity. And I'll skip over these. In the end, having, I guess, been in this business too long, software development has been, it is, and I believe will remain fundamentally very hard. We have been able to build things we could not have conceived of some years ago because we have improved in our practices and our processes and our tools and in our languages. But every time we've sort of overcome those barriers, we realize we want to build more and more complex things. And for many economically interesting systems, the problem now is one of scale, not just computational scale or platform scale, but scale of the sheer amounts of software that we have. Again, Cisco having 30 to 50 million lines of code. Give me a back-of-the-envelope estimate. How much code behind yahoo.com? Any thoughts? Give me an order of magnitude.
Probably
millions. Millions? Millions. So less than 10 million? More than 10 million. Less than 100 million? Less than 100 million, but more than 10 million. That's a scarier number than what Cisco told me. And the challenge is that represents your legacy, a capital investment that you cannot afford to throw away. It's going to be around for a long time. Your children's children will be staring at some of the code you have written and trying to say, what the hell was Dad trying to write here? So you have to ask yourself, given that body of GORP, what can you do to preserve the intellectual design decisions that went into it? Now, here are some things we know about good software development. A guy named Jim Cope has written a great book titled, let's see if I get it right here, Organizational Patterns of Agile Development. Go take a look at it. It's a wonderful book, an easy read, and it's written in the Chris Alexander style of patterns. And in it, he's studied a number of hyperproductive projects and looked at how they're structured. And one of the things he's observed is that in virtually all the hyperproductive teams he's encountered, there's this binary star relationship where you have the architect and the project manager and everybody orbits around these two. And it's recursive because as you have teams of teams, then you have that becoming a subsystem of a largest system and so on and so forth, thus leading to the architectural structures that you guys have in place here. So look at Cope's book because it'll give you some ideas of organizational patterns. Now, as I look at the technical architecture of hyperproductive teams, I find a number of things in common. They tend to have a focus upon building crisp abstractions. You can never go wrong with building a good crisp class or an abstraction. I recognize in the heat of battle, you're going to do some stupid things. You've got to do it quickly. You'll push it out there. But as long as you have a process that allows you to come back and simplify over time, to refactor, then you've got a mechanism in place that will drive you toward a closure of building those kinds of crisp abstractions. Having a system that has a good balanced distribution of responsibilities and a good separation of concerns. These are all the fundamentals, and frankly, the fundamentals never go out of style. We may forget them in the heat of battle, but the companies that are most successful tend to go back to them. This is why at the architectural level I see so many companies like yours trying to do more work upon the governance of your architecture, because it's a matter of imposing these principles upon your system as a whole. There's a fourth one I didn't include here because I've encountered maybe 5 or 6 companies in the world who get to this point, and it's the principle of simplicity. I encounter some groups, eBay does this, where they literally set aside some percentage of their development budget to say, we are going to use this for refactoring of our systems. We are going to spend money to make stuff simpler. It had to be sold to upper management, but the end of the equation says there is value in so doing over the lifetime, because ultimately you are building an architecture that will be maintainable, less brittle, more resilient to change. How do I do that? Well, you know about the RUP and all these kinds of things. They're details I won't go into, but every hyperproductive system I've encountered tends to follow this kind of process. There are 3 pieces to it. Growing a system's architecture through the incremental and iterative release of testable executables. First, the major artifact is an executable. I run across projects that spend too much time writing documents and models and things like that. They're afraid to write code, and they forget that the real artifact we produce is raw, naked, running code. However, the second piece of it is, it's code that is a manifestation of the system's architecture. So what you tend to see is, from release to release, a clear presence of the architecture with more meat getting on its bones from release to release. And last, through an incremental and iterative release of those things, meaning I have the opportunity to make mid-course corrections along the way. I don't want to talk about this. I don't want to talk about that one. Let's talk about this. Some people collect stamps. I collect architectures. So if you go to this site, I've collected about 150 of these, but as part of the handbook project, I've been collecting the architectural diagrams of what architects themselves have described their systems of. This happens to be the architecture of the Canadian Air Traffic Control System, which looks really simple and stupid, but it turns out this diagram doesn't tell you the whole picture by any means. It says, yeah, it's a layered architecture. But the interesting piece is when you start discussing the patterns that are inside this. One of the key patterns is this notion of a mobile object. So the idea is I've got a flight, which is a physical aircraft that moves from space to space. There's a software object that models it directly. That software object actually migrates from node to node in the network as the aircraft moves, and it has this happy side effect that if a particular network goes down, a node goes down, the state migrates to someplace else. So it's kind of self-healing. And in order to understand the Canadian Air Traffic Control architecture, you have to understand its patterns. I'll look at a few others. That's a dull one. Here's an example of some games. If you look at the architecture of games back in the mid-90s, they looked like this. Largely because we couldn't do much with the processors that we had. We could serve up some polygons to a graphics processor, but that was about it. If you move to the next generation, you begin to see a much more complicated diagram, and therefore it's obviously superior. But what this represents is we had more computational power, and so there was an opportunity for doing other things. And if you look in closely, you'll see things like there are boxes for AI, there are boxes for more audio-intensive effects, these kinds of things. You move to, well, actually, I don't have that one, sorry. The componentization has led to the point where you can actually go off and buy pieces. I can go to havoc.com and buy a physics engine. I could go to buy terrain mapping engines and the like. I don't want to talk about those guys here. This is the architecture of the JPL Pathfinder. You'll notice immediately it looks very, very different than the others, because at its core, this happens to be a system that is not event-driven like most web-centric systems are, but it's time-driven. They divide the world into a series of time segments. Some computation happens within those time frames, and there are subframes as well too. You go on to the next one and the next one. Very classical kind of architecture for spacecraft systems. And there are a few others here. To that end, I'm trying to bring this all together in this handbook of software architecture. I've been working on this for a few years. I've got several more years to go, largely because there are so many interesting systems to study, and it's challenging to get to the people that know the architecture itself. Some cases I'm studying source code. In most cases, I'm simply sitting down with the architects themselves and interviewing them to expose the architecture. So go take a peek at the site. It costs you nothing to register. Just give me your Visa number and Social Security number and DNA. But if you have some systems that you think I should cover that I do not have, please let me know. I'd be delighted to do that. Some of the more recent ones that I've begun digs on include the London Underground. You talk about you guys having a legacy problem. These guys came to me and said, we have legacy that dates back 150 years. I said, wait a minute. Nobody was writing software back then. But they said, well, 150 years ago, the first tracks were laid for some of our systems. And we know, and furthermore, the unions got involved, and the railroad engineers and the folks that run the tracks, they have a certain way of doing business. So we know we could do it better, but we simply can't because of this physical legacy that exists around us. I've alluded to this as well, but the work at the Computer History Museum, a few years ago, I approached their board of trustees and said, you guys should become a museum of software as well. Len Chusik and others said, yes, this makes sense. So they have the curator and all. Go visit them if you've got some dusty code lying in an attic someplace that you'd like to donate and does not violate any copyrights or proprietary things in your company. We'd love to get a hold of it. We're grabbing whatever we can. There's an effort right now to get a lot of stuff associated with Fortran. I interviewed John Backus last year, and he's dead now. So this was the last interview we ever did with him, and being able to extract that kind of stuff is absolutely fascinating. And we need to preserve this for future generations, because time is our enemy. Last thing I'll end up with, and then maybe I have time for one question and maybe even one answer. Inside the software group at IBM, I worry about the next 5 to 10 years. There are other people that worry about the next month and the next year or 2 or 3. I worry about 5 to 10 years. And so just to give you a little bit of where my head is in this space, first I'm going to go back in time. And this is sort of where I think we've gotten to. A few highlights in here. The 50s were the time of the rise of the machines. The 70s were the time of the death of the mainframe. Although I got beat up by some IBMers when I said that. So I'll rephrase that by saying the mainframe did not die, it just got sick. But dinosaurs rule, yes. Spoken by the guy with the white beard.
Who does your banking?
Who does my banking? Yeah, right. Very true. At any rate, I don't know where to go from there. We've been in the period of retrenchment. There's talk of sort of a second .NET bubble. I don't know what's going to happen, but we're still at a period of retrenchment, I think. If you look at the next sort of decades, and I went backwards here. Sorry, let me go back here. PowerPoint is evil. Here it is. Where do I think we're going next? I think in the coming decade is one of increasing transparency. This is kind of a conundrum because for most of the world, the software we create is invisible to them. And insofar as it is not invisible, we have failed because the general public doesn't want to see software bits lying around. And so we have to build utterly complex systems that are hidden from view. And I think in the coming decade, that's even more and more so. In the decade beyond that, I think we're reaching the point of almost total dependency, meaning it'll be very difficult for us to live and work and play in Western society without touching software in one way or another. And in the 30s, I think we're going to get to the point of the rise of the machines again. And where I telegraph that is by looking at what's happening in Japan in particular. Interesting economics going on in Japan, demographics going on. You've got an aging population. You've got a shrinking population. The population in Japan is actually declining. And so you've got this bubble of old people and not enough younger people to serve them. So what do? Well, one of the answers is, what happens if you provide automated support for them? You saw the generation of the little robotic dogs and things that were the hit for some time. And if you live in a small apartment downtown Tokyo, you don't necessarily want a pet that poops. You know, not a good thing. So having something that you can treat as a companion, and people got very passionate about these things, there's some value in that. A little creepy value, but there's value nonetheless. Take a look then at what Honda and Sony and others are doing to build humanoid-like robots. And there's a tremendous amount of investment going on in that place to help the aging generation. So that's why I say the rise of the machines. And I need to wrap it up, but I want to say in one last thing here, this is really a fun business to be in. I know that there have been periods, you know, maybe the last several years or so, where especially in the valley, it looked kind of grim. Everything was being outsourced. There was no interesting innovation. It all looked, you know, kind of the same again. But if you step back for a moment, you must realize that we as an industry have changed the world. We have bit by bit, and that's an exciting place to be. What other industry can you think of that has transformed civilization as much as ours has? That's pretty cool. So to that end, as a software developer, it's a tremendous privilege to be a software developer because we do change the world. At the same time, it's a tremendous responsibility because we are changing the future. Thank you very much for having me.